Slowly but surely. There we go. All right, cool. Okay, welcome back. So in terms of like schedule for the class, everything is hopefully turned in, at least all the required stuff is turned in. If you're running behind, that's okay, as long as you're keeping us updated and you have a plan for wrapping stuff up. Don't take, I guess, yeah, if you're watching and you're like, oh, I gotta get this in, like don't take Thanksgiving to do computational mechanics. Like take some time, visit with friends and family, or do something for yourself. You can always get back to it. We'll be back next week. We have time to revise and get to things. There are other things in life other than
the opposite of every other class.
Yeah, I know. Yeah. I mean, it is important, and I do find it exciting and worthwhile. Like it's worth the effort, but I don't think that it's worth giving up like family, friends. Maybe that's just me.
Every other class has major assignments due on Monday after you get back.
Oh, really?
Senior design is the interim.
Oh, it's due Monday?
Monday to get back.
Oh my God.
After that, Tuesday, we test every day.
Every day is an exam?
Every day.
Oh my God.
Sensors,
all right.
Sensors and data, last lab report due Monday. We get back.
Due Monday?
Everything is due Monday.
Oh my God, why? Oh.
So there's a massive gap after Monday and into the finals week. There's nothing.
And then nothing, right?
Everything on the Monday after Thanksgiving.
What? Why? I mean, I know it's like this is a weird schedule because we only have 1 week after. Usually we get 2, so there's kind of like a week of doing projects and finishing things, and then a week of review. But this time it's all like everything, like review and projects are all the same time. But I don't know. We're ahead of the game. We did all the work in the beginning. Like we've been doing projects throughout. So yeah, we don't need to stress. We're good. Sorry, was there a question?
Yeah, this week start out this year? I don't think so, right? So that means we not actually lost 1 week compared to the last 3 years.
Yeah, so we still had Thanksgiving ended up being like later compared to when we always start.
The school week.
No, it's still like 15 weeks of the semester. It's just that 1 week break got shifted to week 14 instead of week 13. Yeah, kind of a mess. Yeah, so I juggled for a while, but with the thought of I don't want Thanksgiving to be project time. The goal is get steady work until we're just done at Thanksgiving.
Do we have access to all the stuff we've done after this course is over? Can we basically log into NanoHub and then all these repositories or all these modules are available?
Yeah, and so NanoHub, like we keep logging in and using our CompMech tool, but there's a ton of other tools too. Like you can also just like log in and use Jupyter.
Well, because next semester I'm doing some coding work for my independent study, and I'm going to be doing Monte Carlo.
Okay,
so
perfect.
My question is, do we still have access to this afterwards?
Yeah, okay. Yeah. So if I launch like the Jupyter notebook, and that's like on the homepage of NanoHub, I think one of the folders in there is like a CompMech folder, because I think this is like kind of a tool for Jupyter.
Gotcha.
I'm trying to remember. Yeah, so here, like I have a CompMech folder and a Dynamics folder for like the 2 classes that I have tools built for.
Okay.
And there's different like revisions that I have. I think we're all working on 111. That's a weird. Why is 118 118 111? Anyway, I think we're all working in this 111. So yeah, this is, and that's one of the reasons that I wanted you to like sign up for this NanoHub account, is that it's an external personal access to Jupyter, and you can use it forever. I think because it's run by Purdue with National Science Foundation stuff. Like, I don't think you could deploy a notebook and then start charging people to go use that notebook from this server. Like, you can't use it to generate income, but you can do analysis and then profit from that. Like, yeah, kind of a weird, like, gray area. But if you're doing calculations and getting paid for that work to do that, I think you could use this tool for, but I don't think you could charge someone to use this tool like through you. But if you want to get deep into the weeds of like free and open source software licensing usage. Cool. What else are we working on today? 5? Homework 5?
Not quite there for me, but yeah.
But yeah, like module 5 kind of look stuff. So like the goal of like coming back into module 5, kind of, we're not redefining derivatives at all, but we're just like taking a deeper look into like what is, when we approximate a derivative with like a delta x or a delta t in that denominator, what else can we do with that? So in module 3, we're using initial value problem solvers, and if you know everything about like something at like x equals 0, then you could integrate it. Like if you knew the fixed boundary condition and the slope, then you could solve for the rest of it for a second order. For something like this, like a heat fin, where it's a second order differential equation, and we could solve that steady state problem. It's like, okay, I know T0 is this temperature, and I know the slope is something. But normally we don't know that. We know something about like the temperature on one end and maybe the boundary, maybe like the slope on the other. So heat flux is a slope dependent, and then heat, like if you have a heat sink, that's temperature. So like fixed temperature versus fixed, like 0 slope of temperature. And finite difference, it's similar to finite elements. Like if you can understand like finite difference method, finite element is the same thing. The only difference is like instead of splitting everything up into node locations, you start saying like, all right, this is my element. Inside that element, everything is either linear or quadratic. And then it's something called a shape function. But the equations end up looking the same way, where you have something, each element is defining either forces or temperatures or something like that. Just as a mile high view, like why go back to this? Why revisit? Cool. I'll check in, see what we're up to.
Still going back to what we did.
Yeah. Okay.
What you sent made sense.
Yeah.
Because I was taking the first derivative of one step forward,
That's
but it should have been 2 steps forward to make it match. Basically.
Yeah, so that's what I did at first, and then I can't be right, because you're looking for a second derivative at a given point.
Yeah, I was taking a different point for the first derivative.
Yeah.
So that makes sense.
I don't really take much for the modify this one step first.
Okay. Yeah. Are you looking at yeah, nice.
This just one thing about the interesting. So one that one getting because they're not using that same tradition. We're using that before the end.
Yeah, so if you're like with central difference, if you try to take like the first derivative, you lose like 0 and like -1, and if you try to do it again to get the second derivative, then yeah, now you have 4, 2 and 2. But the central difference, like the definition for the second derivative of that central difference, still only misses 2 values. So if you use that definition, you lose 2. No, because it ends up being like the forward, backward, and central difference all have the same definition for what a second derivative is. You're using 3 points to approximate the parabola, and then taking 2 derivatives of it, so you just get one boundary.
Instead of 4.
Yeah, but you're still missing 2 because you're using yeah. Yeah, like so they all have the same definition, so they almost look like the same functions, just shifted by one concept. Forward starts at 0, central starts at 1, second, or backward starts at 2. Yeah, and then each of them go to yeah, because some people try to just try to do a first derivative, a fourth derivative is just the first derivative 4 times. So you miss, but then you're truncating, like keep chopping off more and more points every time you do it. You end up with a single value for that fourth derivative.
Yeah. That's what.
That one, no, 12, 6 is Friday. But yeah, so I thought it was like that's but if they have a plan, okay,
yeah, because when terms over, your contract's over. Yeah.
Well, that's fine, but I mean, that was, you know, that was just more like, well, no, I feel like some students are like, they like, I don't know what to do.
Yeah, and then for this last one, usually, like, we were just talking at the beginning of class, that some people have 3 projects due one day when they get back.
Yeah.
And then finals all week.
Yeah.
And then finals week then. So they're not gonna have time because but if they ask them attention, then they do it finals week.
Yeah. So what do you think, like, what is the best way to, I mean, I don't know if you want, like, I'm happy to do it, but I'm,
Yeah. Well, I'll explain again, like when we get back, all that, on Monday, I'll say, this is the plan through Friday. Can't get Friday. The following Friday of finals, is our last. We need stuff by then.
okay.
Okay. All right, yeah. How to do questions. Yeah. And that's the same kind of process as the rest of the notes. It's gonna be late, that's okay, that's also. Yeah. Yeah.
I just feel like you guys mentioned they're reading around.
Yeah, because now it's like hard.
Yeah. Everybody else is.
Yeah,
Yeah.
3 weeks. Well,
Yeah.
sorry.
Yeah.
I can't help with it.
At this point.
Yeah, and there's always like field choices where.
Or, yeah.
Something, yeah. Usually that's like between.
Yeah, I mean, I was. Even. Yeah. It's not long term.
It feels long, right?
August.
Yeah. Yeah, Thanksgiving so late, so it feels like just let us go. Let's call it. Yeah. Oh, okay. Yeah. So, yeah, some people interpret that different ways, but like in practice, like if you have this, if you build this thing and you apply a force, 0.2, the 0.2 is going to be a positive number, whether it's left, right, up, down, so that. Yeah. Oh, no, the weight is like, if you take density of aluminum times 300 millimeters times area times 11, so we have 11 bars that are heating up. Oh, yeah. Yeah, they're all 300 millimeters. What did you get for East Coast? 23. What was the total? Yeah, now it's all just like guessing. Okay. Yeah, so right now, so if you know that this is current, so for this area, this is just like, because 10 times more area, 10 times less reflection. pretty much the same thing. I basically multiply by 1, which is 0.98. Yeah, you can do it down any with guess and check like we have the Epsol routines, the set time method. You can set up a function that returns 0.2 minus that selection at p5. It is still a guess and check method. Every number is still a guess and check. Just that one. But yeah, for the most part, Steve without 8,000.
Question. Yeah. So when I was plotting the difference between forward and backward difference methods, I found no difference. Because right now this is the forward difference in shifting your numerical solution to the left. Okay. But when I'm doing backward difference, at least when it comes to the equation in Python, you don't see a difference. Actually writing the equation because it's f of x minus f of x minus 1. So it's basically taking index 1 minus index 0.
Yeah.
Over your time set.
Yep. Yeah.
So there's no difference between forward or backward difference.
No. Yeah.
So in terms of the graph, it shouldn't shift. The shift is the same, or should it be different?
The shift is different because
You have to start there. So when you plot, you have to start. Because I started it at 0. It can't be started at 1.
yeah,
And then go to
go to this one, you go then.
okay, so that's a shift.
Yeah.
So backward difference shifts it forward, shifts it to the right.
Yeah, exactly.
And so this is going to be the same for the second derivative. Or instead of starting at 0, you start at 2. You go to 18.
Yeah.
Okay. So it's the same equation, but it's just a different starting points.
Yeah.
Okay.
It ends up being for forward, backward, central, ends up being the second derivative happens to be the same equation, like the exact same equation. It's just evaluated either at
points.
Yeah, x equals I minus 1, or I plus 1.
Makes sense. Thank you.
Yeah.
So we're talking about,
Which one is central? Are they both forward?
oh, whoops. Yeah, one of
One
them
backwards.
backwards. There we go. So we were talking about like taking these numerical derivatives. So in this case, like looking at a cosine wave, or sorry, a sine wave, one derivative of that is going to be a cosine wave. So I know that analytical dy dx is cosine of x. And then forward difference and backward difference. In terms of writing, like what does the code look like? Let me grab that forward as well. The forward and backward definition, like what is a forward derivative versus a backward finite difference, it look exactly the same for both for the first derivative and for the second derivative, because we're only indexing like values of known values here, which is kind of weird that like, well, it's two different definitions, but relative values of like, am I talking about I plus 1, and I plus 2, or I minus 1, I minus 2? Same thing, like we're still using the same bucket of y measurements and x measurements. The only difference comes when I go to plot this with a forward difference. The very first derivative that I have is at 0.0. So at x equals 0, I have a derivative there. But with backward difference, I can't start at x equals 0. I start at x equals 1. And then, oh, I'm looking at, oh, that was the second derivative. Yeah. All right, so let's look at second derivative too. So dy. And same thing for like that second derivative when I start looking at d squared x dx squared. I can calculate a second derivative at x equals 0 for forward, but I can't do that for backward. I have to wait until 2 time steps later so that I have the current plus 2 behind it. And that's the main difference between like forward and backward. It's like how many steps we need to look at. Oh man, it doesn't like that one. There we go.
We put latex in print statements.
Yeah. So if you use like an R, I forget what that R does, but it makes it, there's something about like when your labels are R quotes that now it can recognize LaTeX.
Is that only for labels on plots? Or is that any kind of print statement?
No, we could also say like, if I do the formatting correctly, then it works. I don't know why I put the, oh, I put a plot. I meant to say title. So you can do like titles, legends, even your axes, like we could.
And it only works in the matplotlib function, or could you just do a general print statement?
I don't know if you can print LaTeX. Let's give it a shot. So in printing, that one would not work, but yeah. But there are like pretty print things that work well with LaTeX. Like SymPy. Like if you're trying to do like print out like nice equations, SymPy is a nice way of doing that. So if I just want to show like sine of x, just print it out. I can create a function, here's sine of x, and then even take like, I think dot derivative, like that. I don't know. No, not derive. I want diff. Oh, it is just diff. That's confusing. So I can get like, here's my function, take a derivative, show me, at least if I want like printed LaTeX kind of math statements. And then this output you can show like as a tech command.
Can a markdown cell, are you able to reference code from the previous, like if you wanted to basically print out a nice paragraph of something, but it referenced a solution or output from one of your previous actual coded cells?
Yeah, so there's a professor, he taught thermodynamics and a couple of, Professor Weber, he used to do that.
So it is possible.
Yeah. Markdown cell reference Python variable. No. Inline variable insertion. Oh man, how did he do that? What was the end result? Long conversation. Missed markdown. Oh man. I don't remember. This is showing like a kind of a hack to get it to work. So it looks like you can import markdown as MD. So you can import, like at least you can get outputs that are markdown, like you were saying. And I think now we could say stuff like I don't know if this will work. Yeah, it didn't like that one. I don't know if we could get equations in there. Yeah, it doesn't like that. The equations, at least. But we can't get markdown. Oh, use LaTeX function, display and math. Oh, thanks. Display. Import markdown. Display math. I don't know how to do that one.
I think
What?
you're still calling MD.
Am I supposed to use display?
I think so.
Something like that one. I don't know. I think it is possible. I just, yeah, haven't gotten it. Oh, math that way. I see. So this is a math equation. So you can mix and match. We could say MD of hello world, and then math. Oh, but it only gives us one output. I don't know how to display. Oh, maybe that display was the thing that we needed. Little. Look at that. Ooh, nice job. Thanks, M. Cool. So you can do, like you can, I guess you could, that would be a nice way of like, if you wanted to have generated cell content, you could create some variables and then tell it display this stuff and substitute in. Like that would be great for reports.
Yeah.
Like if you were doing that New York Stock Exchange data, but you wanted to update it every morning, so you have like a little report to send to people. Cool. Yeah, that was a fun little experiment. So markdown, display, and math. We can kind of mix and match those. Display, markdown. I don't know how to get those like fractions and stuff to work in the math display. I'd have to check documentation. Oh man. So that .md is missing from homework 5. Sorry about that. All right, cool. thanks for joining, and we'll be back. Get a week off, come back strong, and finish out the semester. Yeah. Good luck, senior design. Thanks a lot.
Have a good holiday.
Thanks, you too.